Hello, everybody. This is Sunday, it's July 10th, and we are heading into week 10 of our online astronomy course. Now, before I get started, I'll tell you the astronomy news, and the astronomy news is that we are only a couple days away from the release of the first images from the James Webb Space Telescope. That's going to be released on Tuesday morning. And so the next video, I'll be telling you all about those images and hopefully sharing some of them with you. So all astronomers are just waiting for these images. We waited 10 years, for James Webb to be developed and to have the telescope successfully launched. It went through so many problems and it's working flawlessly. But on to Module 10. In Module 9, you learned about the sun, how the sun is just a big ball of gas, mostly hydrogen and helium. You learned that it's powered, it's shining because of the nuclear fusion reactions that are taking place in the core of the sun. And that's what stars are. All stars, like those you see in the background behind me, are big balls of gas, mostly hydrogen and helium. And they go through cycles that we're going to be learning about. They have a life cycle just like a person has a life cycle. And we'll be finding about that in some of the later modules. But this module is about how we know everything we know about the stars. I mean, even with JWST, the James Webb Space Telescope, all we can do is see stars as individual pinpoints of light. We have barely managed to see some surface features on the most giant stars. But otherwise, stars are just little points of light. But yet we know so much about them. And I want to tell you how we know some of those things. And that's what Module 10 is all about. And the first thing to think about is one of the most basic things you could know about a star. How far away is a star? If you're looking in the night sky and you might be looking at the constellation of Orion or the constellation of Sagittarius, and you see those star patterns, all those stars are not at the same distance from us. So how can you tell the distance from a star? And the way that we do that is using a surveyor's technique called parallax. And the idea of parallax is that if you look at something from one point of view, and then you change your position and look at that same object, it lines up with different things in the background. And that shift in the apparent position of something close relative to objects that are distant in the background, that shift is called parallax. And I want to demonstrate it here for you. So what I want you to do is, make sure that the screen is at least several feet away from you. If you're holding an iPhone or something like that, watching it on that, hold it at an arm's length so you're not right up against it. And the whole idea of parallax is that we're going to look at stars from two different positions. And to find the distance to the star, we want those two locations to be as far from each other as possible. Now, what's the farthest you can get for two people making an observation on Earth? And you might think, well, one's on one side of the Earth and the other one's on the other side of the Earth. That's pretty far away. And that's true, but we can have the two observers much farther away. Because as we know, Earth orbits the sun. So at one time, if the sun is on one side, if Earth is on one side of the sun and makes an observation to a star, and then you wait until 6 months later when the Earth is on the other side of the sun, it can look at that same nearby star and see it shift its position relatively to the distant background stars. So as I said, I want to show this to you. And so you should have the screen at some distance from you. And we're going to pretend that your eye, each eye represents an observer on the Earth. And your nose represents the sun. So if you're looking out of this eye, and the other eye is closed, you're looking when Earth is on one side of the sun. 6 months later, Earth is on the other side of the sun. You're looking through the other eye at that same object. So here, hold out your thumb, just at elbow's length, hold out your thumb, and maybe cover up one of the stars you see behind me in the background. Just cover it up and look through one single eye. Doesn't matter which eye it is, just look through one single eye and cover up that star. So that's an observation made from one side of the sun. Now don't move your thumb, and the background's not going to move. I just want you to change eyes. That's like waiting until Earth is on the other side of the sun. So change eyes at 6 months later, and now, is your thumb still covering up that same star? No, it's not. Your thumb didn't move, the distant star didn't move, but your point of view changed. And from knowing how large that shift is, that parallax shift, we can find the distance to some of the most nearby stars. And you know, it's surprising how long it took us to find the distance to a star. This is an old astronomy book that I want to show you. It's an old astronomy book. It was published in, let's see if we can get to the page here. Okay. So here is the name of it. This is an introduction to astronomy. It's a textbook for the students of Yale College. And it was published, maybe you can see down there on the bottom, in 1839. That's 183 years ago. And so this book is talking about astronomy. That's all the book is about. So I'm going to open up the front of the book. I want to show you that this much of the book right here, this much of the book that I'm showing you, is about the solar system. The planets as they knew them then, they didn't know of all the planets. The planets, the comets, meteors, or they weren't sure what meteors were, asteroids. The first asteroid, I don't think, had been discovered in 1839. Maybe it had. I think it had. One of the brightest and largest of the asteroids had been discovered. But this much is about the solar system, and only what's left is this much right here. That's how much they knew about stars and galaxies. And so here is a chapter on the fixed stars and the system of worlds. And so you're reading along here about the brightness of stars. You talk about the constellations, still nothing about what a star is. And they never do tell you because they don't know what stars are. But you get to a point where they're talking about the distances to the stars. And they're saying how these stars are really very far away. And we have said that stars have no annual parallax. They looked for parallax, they looked for the shifting, but they couldn't find it. But then, as this book was going to the printer to be printed, there's a footnote at the bottom of the page, right down there, one of those footnotes. And let me read it to you. Very recent intelligence informs us that Professor Bessel of Königsberg has obtained decisive evidence of an annual parallax in the star 61 Cygni, amounting to 0.3136 arcsecond. That's about a third of an arcsecond. An arcsecond is 1/3,600th of a degree. So if I cut a degree in the sky, just an angular degree into 3,600 parts, one of those would be an arc second. And this shift was a third of an arc second, so very tiny. But to go on with the footnote, this makes the distance to that star equal to 657,700 times the sun's distance from the Earth, a distance which would take light 10.3 years to traverse. And so right there is the announcement for the first time of a distance to another star, 1839. 10.3 light years, too, is very close to its presently accepted value. So you'll learn all about how astronomers use parallax to measure distances to stars that are relatively close to us. And also, we're going to need a new unit of distance to talk about stars. I mean, if you talk about distances on Earth, you can talk about kilometers. If you talk about distances of the planets from the sun, you might talk about astronomical units. You know, 1 AU is the distance from Earth to the sun. But for the distance of Earth or the sun to the nearest star, there we need a new unit. And we call it a parsec. Okay? A parsec is 3.26 light years. A light year is just a distance light travels in a year, and a parsec is 3.26 times that. A parsec is the distance, has to do with the distance that you would see Earth's orbit, how far away you would have to see Earth's orbit occupy just 1 arcsecond of distance. That's a long distance. So parsecs are made for talking about distances between stars. The nearest star, Proxima Centauri, is a little bit over 1 parsec from Earth, a little bit over 3.26 light years. You know, I could tell you how far in kilometers, but it would be so many 100,000. And you know, once numbers get that big, you're really not using the right distance unit anymore. What else is coming in module 10? In module 10, we're learning about the distance, the relation between a star's brightness, that is its luminosity. A star's luminosity is how much energy it gives off every second. The relation between its luminosity, its radius, and its surface temperature. And that's going to be a handy tool we'll be using to understand the stars. Another question you might ask about stars is, well, how bright are they? Well, I mean, if you're going to rank stars, you know, if you want to know who's the fastest runner, you might have a race, and there's a race 100 meters maybe. And at the end of the race, you know, whoever's the fastest, you know, you call her first place. Second runner, you know, the first runner-up might be second place. Third runner-up might be third place. Well, we do the same thing with stars. The brightest stars in the sky occupy first place. And we call those magnitude 1 stars. So magnitude 1 is the brightest stars in the sky. Now, who invented this system? This was a long time ago in ancient Greece. And so this is a system we've inherited from the ancient Greeks. So 1 is the brightest star. On the other hand, 6 is the dimmest star you can see with the naked eye. So magnitude 1 are the brightest stars. They won the race for brightness. 6 magnitude stars came in last place, 6th place, and they're the dimmest stars you can see with the naked eye. And, you know, 6 minus 1 is 5. And so what does that mean? If a magnitude 1 star is, you know, 6 times, magnitude is is a difference of 5, 6 minus 1 being 5. It has a difference of in magnitudes of 5 from another star. What does that 5 mean? Well, a difference of 5 magnitudes means a factor of 100 in brightness. So a first magnitude star is 100 times brighter than a 6 magnitude star in the sky. But we've inherited the magnitude system and from the ancient Greeks, and as we've developed more sophisticated ways of measuring the brightness of stars, we've tried to adhere to those measurements that were made long ago, even by the Greeks. And so magnitudes that we measure today are in pretty good agreement with those that are made back in the times around 600 BC by some of the very first people to make star catalogs, people like Hipparchus. So you'll learn about magnitudes. Now, what does a magnitude tell you? If I see a first magnitude star in the sky, well, that's great. That means it's one of the brightest stars in the sky. But why is it bright? Is it bright because it's really luminous? It gives off a lot of energy per second? Or is it bright because although it's dimmer, it might be really close to our eye? So it just appears to be bright. Now, the stars I was talking about before, where 1 is the brightest, 6 is the dimmest, those stars, based upon how bright things appear in the sky, is called an apparent magnitude. And apparent makes sense because we're talking about how bright stars appear in the sky. But suppose you had all the stars at the same distance. Suppose you could, just pluck one out of the sky and bring it in to a certain distance from you. And you could reach out and grab another one from the sky and bring it in to that same distance. Then you could tell which one is really bright because all the stars would be at the same distance. And we call those absolute magnitudes because those absolutely tell you what stars are brightest. And an absolute magnitude is the magnitude a star would have if it were a distance of 10 parsecs away. Now, what good is it? I mean, what do you get out of knowing a star's apparent magnitude and its absolute magnitude? Well, you'll find out in this module that there's a really simple formula that you put those magnitudes into it, and out comes the distance to the star in parsecs. It is extremely powerful, and it's the way that we know the distance to the closest stars. And we'll be learning more about that in the next module. We find out how you can know the star's absolute magnitude without knowing its distance in the first place. So you'll be learning all about that. And once astronomers know the distance to the star and they know how bright it appears, they can figure out how much energy it's really giving off because they can take distance into consideration and figure out how much energy the stars are really going off. That means they can figure out the star's luminosity, actually how much energy per second it's giving off. They can also measure the temperatures we found out from its spectrum. And there's a wonderful history of astronomy in people interpreting the spectrum of stars, those dark absorption lines you see on the rainbow continuous spectrum of a star. And there's a series of amazing women who worked at Harvard Observatory that figured this out. That they started out just calling stars, by some category. They called stars A stars, B stars, C stars, K stars, M stars, all sorts of things. And then as they studied them further, they rearranged the order. So the patterns would flow into one another very smoothly. And it was discovered that this ordering of the categories of stars was a temperature sequence. And the pattern turned out to be O, B, A, F, G, K, M. So that is called the spectral sequence of stars, O, B, A, F, G, K, M. And O stars are the hottest. M stars are the coolest. And so O, B, A, F, G, K, M. Generations of astronomy students have learned this by a little saying, and it is, "Oh, be a fine girl / guy, kiss me." And so, OBAFGKM, O be a fine girl / guy, either one, depending upon whatever your preference may be, kiss me. And that is how you remember the spectral sequence. What else can we get from stars? Well, we've already learned about the Doppler shift and the spectral lines. We learned about that, how spectral lines, if an object is moving away from us, its wavelength is stretched out and becomes redder, stretched to a longer end of the spectrum. And if it's coming toward us, it is stretched toward the bluer end of the spectrum, those Doppler shifts. And we call that stretch the movement of the wavelengths toward the longer wavelengths, toward the longer reddish wavelengths. We call that a red shift. And we call the shift of the spectral lines toward shorter wavelengths a blue shift. So we can find out the velocities of stars, how they're moving toward or away from us. We can find the masses of stars by watching two binary stars orbit each other. And as they orbit each other, we can use Kepler's laws, as modified by Newton, to find out the masses of the stars. So we have a wealth of information about stars. And we have to organize that information somehow. And I want to show you how we organize that information. And to do that, I'm going to pull up an important diagram that astronomers use, and it's called the Hertzsprung-Russell diagram. And there it is, a Hertzsprung-Russell diagram. I'm going to move to one side here so you can see it a little bit better. Now, what this is a diagram, and each point on there shows where a star is. And what it is, you can plot a star's temperature. And notice what you have here along the bottom of the HR diagram. You have on the hot side, O, B, A, F, G, K, M. There's the spectral sequence of stars. Notice that hot stars are over here on the left, cool stars are over here on the right. O, B, A, F, G, K, M. And you can see the surface temperatures of the stars about 30,000, over 30,000 degrees for the hottest stars, down through 10,000. Here's 6,000. That's about where our sun is. Our sun is a G3 star. Can't remember, G2 or G3. And then KM for the coolest stars. So the temperature is plotted along the horizontal axis here. Now along the vertical axis is the star's luminosity. And a 1 right here means that this star has the same luminosity as the sun does. Here is a star that has 10 times the sun's luminosity. Here is 100 times the sun's luminosity. 1,000 times, 10,000 times, 100,000, much, much larger. And these stars down below are stars that have less than the sun's luminosity. So here's 1/10 the sun's luminosity, 1/100th, and so on. So every star has a position in the HR diagram. But about 80 to 90% of the stars start out up here. And they occupy this band that goes down here and then down. This band It's called the main sequence. You can see right here, the main sequence. Main sequence starts up here, goes down, down. 80 to 90% of stars are on the main sequence of this diagram. Now we better give this diagram a name if we're going to talk about it. It was first plotted by Henry Norris Russell and Einar Hertzsprung, and it's called a Hertzsprung-Russell diagram, or just in short, HR diagram for Hertzsprung and Russell. So this main sequence is where about 80 to 90% of the stars on the Hertzsprung-Russell diagram are. They have something in common. What they have in common is all of these stars are changing hydrogen nuclei into helium nuclei in their centers. And if you want to know where the sun is on the Hertzsprung-Russell diagram, maybe you can see it. It's right about there, where it says sun. Now, what happens when a star runs out of hydrogen? Then a star's surface characteristics change. They become brighter, they become cooler, and the star moves into the red giant part of this diagram. The most massive stars move up into the supergiant part of the diagram. Now, of course, the stars aren't moving through space, but their surface characteristics, their brightness and surface temperatures are changing so that their position on this diagram is what's changing as they move up. Ultimately, though, they run out of fuel and they become white dwarf stars. Here are these stars. They're only about the size of Earth. These stars have no fusion going on in them, we'll learn. But this whole story of how a star changes in its lifetime is the story of stellar evolution. And we're going to talk about how a single star's surface characteristics change, how its interior structure changes as we go through the modules to come. The next couple modules, modules 11 and 12, will tell us about the life stories of stars, all the way from very young stars on the main sequence to the end products, which are white dwarf stars, neutron stars, and black holes. So we'll be talking about all of that. So, fascinating stuff. Stars are have a fascinating variety to them. I think you'll enjoy learning about them. I certainly hope you will. And before we do, I do have to take a look at Stellarium. So let me just pull up Stellarium here. Here we go. And this is set. We are out. This is, whoops, I didn't want to do that. This is out on the 14th of July. So this is midnight. So this is either very late Wednesday night or very early Thursday morning. We're looking southeast and we are looking at the moon. Now, this is a full moon. Wednesday is the day of the full moon. And so this is the first night you can really see the full moon. And the full moon is happening, this full moon is happening at perigee, when the moon is closest in its orbit to Earth. And so this is a supermoon. This is the biggest the moon will appear in the sky. And so it might be cool to go out and see that. If you just look in the southeast, remember the full moon rises fairly late, so you have to go out late. You can go out 11 on the 23rd or the next midnight. But if you wait a couple nights past then, if we go to the 15th, which is Friday, or the 16th, which is Saturday, you'll see the moon passing by Saturn. So that's something to watch for too. So I will warn you that this module is one of the more mathematical modules. But as you know, the math is always confined just to the homework quizzes If you take a look at the course, at the introduction for the module, I work examples of how to work the problems you'll find on the homework quizzes, and on the exams, you won't have to do any of that math on the exam. So please don't worry about it. But I do want you to understand how we know what we know about the stars. So I hope you find out that you enjoy learning about the stars. It's a fascinating story. And next time, I'll be talking about the JWST images that are going to be released on Tuesday. I will start talking about how stars live their lives. So until then, I will look forward to seeing you next time. If you have any questions or just want to talk or whatever, you can always email me, or we can set up a Zoom meeting, or you're welcome to drop by my office. So I'll look forward to seeing you next time. Bye-bye.